Hi, welcome back for part 2 of second stage blink on steroids, so to speak. In this video, we're going to look at some of the spec sheets for the components we used in first part of the video and in this video. And at the end of the description, I will provide links to pretty much most of the components that I've used here, or equivalents. So let's get started. Okay, I've turned the light off so that we can see what I'm looking at here. On the left, what we have is another MOSFET, very similar to the ones we had up here and here. This one's a different part number. This is on a board that I got from eBay. They don't cost a lot of money. I'll provide a link to it. It has an opto isolator and the opto isolator is on, where am I? Here we go. We have an opto isolator. I don't know if I can zoom in. There we go. We have an opto isolator and we have a full wave bridge rectifier in here, as well as the MOSFET, some resistors as well. And what this is you can drive this from this lead here. It doesn't matter which way round you put the power into it, but it does need 12 volts. So you could connect this to one of these transistor outputs as the load. You know, just use the little 2N2222 as the load. And then you could switch some very high current. This will do about 20 amps or something. It's rated, the transistor is rated at, the FET is rated at quite a few volts, way more than what the board can handle. But this board, as a limitation of the circuit board, will handle about 20 amps and easily handle, say, 28 or 48 volts for, say, the heated bed of a 3D printer or some other heater or something like that, very easily. But you do need 12 volts, so you'd have to use an additional transistor to buffer the signal a bit. This device here is another MOSFET. This basically inside is pretty much the same as these little ones here that we had before. Only this one is much higher powered. But the same principles work. We'll go through the specs of them in a moment. This last device is kind of a special one. This is what they call a solid-state relay. It'll take on its input anything from 3 to 32 volts. And so even an Arduino Uno or an Arduino IoT33, which is only a 3.3 volt system, etc., can drive this without any additional circuitry. You don't even need to have any limiting current resistors in here either, because they're already built in, and it'll take any input from 3 all the way up to 32 volts. Its output is completely isolated from the input, and in this particular case, this will control 280 volts at 50 amps. That's a lot of power. That's about 10 kilowatts. 5's 10. Yeah, anyway, it'll switch a lot of volts. It's an AC switch, though. You can't use this with DC. It'll switch AC, so for controlling mains and things like that. But a very useful device. You can screw it to a panel or something. You know, if you're using it its full load, it will get warm, so you'd need to dissipate the heat onto a heat sink or something like that. And then you just use screw terminals to hook everything up. So it's very easy to use. It is, you know, for mains, so you've got to be aware of what you're doing when you're handling mains. But a very useful device in a lot of cases. MOSFETs are great for handling DC. In some cases, with the right schematics, they will also handle AC as well. But you've got to configure them in certain ways to do that. And again, beyond the scope of this video. But let's have a quick look at some of the data sheets of these so you can see what kind of loads we're able to handle. All right, so let's go back here, bring up my browser. There we go. Okay, this is the kit that I'm using parts from right now. It's the from Elegoo. It's the Elegoo Uno Project Superstarter Kit with tutorials for Arduino. I haven't gone through a lot of the tutorials yet, but I'm expanding a little bit on software, a little bit on hardware. So I'm basically giving you other examples that are similar to the tutorials but a bit more involved. So in this kit you've got the Uno, you've got a whole bunch of LEDs, you've got transistors, these are the 2N2222s, you've got beepers and all sorts of stuff, motor controllers, you name it. There's quite a few different components in here for doing projects. We will be going through all these different types of components in future videos. Anyway, that's what we're using as the microcontroller. Now, as far as the external components are concerned, here is the MOSFET driver that I got from Banggood. And if I go up here, this one costs, there you go, $5.72 Canadian. All right. It'll handle, where's the specifications further down, probably 25 amps in there. And that's the actual MOSFET is capable of more, but the limitations of the board, etc., they'll limit you to about 25 amps. And it will easily handle 24 volts or even probably 48 volts without an issue. The input, though, to trigger it will require certainly more than 5 volts because of the drops against the optoisolator diode plus 2 diodes in the bridge rectifier. You would need probably in excess of 5 volts. I did try it with the Uno and it wouldn't switch it on and off successfully. So you really need something like a 12 volt supply to drive that thing. The next one is the bipolar transistors that come with the kit. You can see these are capable of switching. Now these are maximum ratings, not normal ratings. So you can have up to 40 volts across the collector and emitter, which means it can switch up to a 40 volt load. I would actually probably prefer to keep that down to about maybe 24 or so in normal use, because that's all you really will come across in most cases. But it's capable of going up to 40 anyway. The base emitter voltage can go up as far as, sorry, let me get this right. Remember I was saying that the transistor, bipolar junction transistor, is like a diode. Well, this junction between pin 2, which is the base, and the emitter, which is on pin 3 here, this is basically a diode, and its forward voltage is still going to be 0.6, 0.7 volts or something like that. Its reverse voltage here is what is the 6 volts. If you connect it incorrectly and put 12 volts across that junction, you're probably going to fry it. It will handle a maximum 600 milliamps. You probably don't want to run it that high because it will get very, very hot. And it will dissipate about 625 milliwatts. I would show you some measurements about what happens with a transistor when you vary the base current and things like that as far as quirks, but I'm going to save that for another video because it'll just complicate things right now. But stay tuned, I will be doing one. It will be quite interesting, I think. So the DC current gain, which is usually referred to as HFE with the BJT, bipolar junction transistor, they have a curve tracer device that can profile the transistor, and the gain is different depending on how much current you're passing through the collector versus what you're putting into the base. So you can see here this little table, 0.1 milliamp, 1 milliamp, 10 milliamps, etc. And there's some temperature differences here too. The gain changes from 35 up to about 100. This is minimum gains. It can have more gain. Minimum is these. If we go to the top of the table, you can see minimum is this, max is this one. So they're saying you're going to have a minimum gain of these depending on what your current you're flowing through. Now, in the board where we had the LEDs turning on and off, so right here, these ones, these are only passing about 10 milliamps through those. We're passing about 10 milliamps, so here we got about 10 milliamps. We're just a little, we're actually only using 5 volt collector emitter. So you're only going to get about a gain of about maybe 50 to 75 on this. Now, the other important parameter is the collector emitter saturation. You can use that to kind of figure out how much power you're going to be dissipating in the transistor. So if you're passing a 500 milliamps of current through the collector, then it can have as much as a full volt on across that collector emitter as well, which means that you're going to be dissipating 500 milliwatts of heat in there. And if you look back up here, the maximum power rating is 625. So you're going to be getting close to the maximum power dissipation capability of this device when you're using it. Anyway, I won't go into any more than that. Just suffice to say that those are, basically that little transistor is capable of switching a reasonable amount of load. It can actually switch on one of these big LEDs if you want it to as well. All right, next one, the 2N. This is the MOSFET. So this is actually the baby of this set, although there are some distinct differences with a MOSFET compared to a BJT. So first thing is it's a 2N7000, which I've mentioned. It only has a maximum current of 200 milliamps. It will handle more volts though. Let me go down here. You can continuously pass 200 milliamps. You could pulse up to 500 milliamps. For what we're doing, really just go off of the continuous rating. It's only 350 milliwatt dissipation, not the 600 nod of the BJT. And the other important parameter for a MOSFET is its gate threshold turn-on voltage. This is the voltage that you need to apply to the gate relative to the source to get it to turn on. So here's a symbol for this N-channel MOSFET. And you can see, here's the gate, it's isolated, and it's the volt between here and here that determines when this starts to turn on. You can see here it'll handle 60 volts, mentioned that, 200 milliamps through the drain to source, and its RDS on, which is the resistance between the drain and the source, is 5 ohms, which means if you're passing 500 milliamps through 5 ohms, that's about 2.5 watts of dissipation in that. That's way exceeding the 350 milliwatts that you're able to normally switch with this thing. So you need to be a little careful with this little device. This RDS on of 5 ohms is not typical of a lot of modern MOSFETs, but this happens to be the one that we were just trying here. The last thing is the gate threshold turn-on voltage. So I'm just going to find that parameter. Here we go. Gate threshold voltage. Right. So this is measured when the drain starts to pass 1 milliamp of current through it. That's how they determine the gate threshold for this particular device. And it's anywhere between 0.8 volts and 3 volts. You can exceed 3 volts, of course, but it won't be, it's when it's starting to turn on. So you can see why this is ideal for driving from something like a little microcontroller as used in the Uno R3, etc. Because it'll easily output 3 volts. And even if you're using some of the newer devices that only run at 3, they're probably only outputting, say, 2.5, 2.8 volts on their pins, but that's still more than enough to turn on the MOSFETs. Okay, and it can turn on, turn off delay times. It can do it in about 10 nanoseconds. So it can switch pretty quickly if you want it to. The next one we used is the 76137. This is from Fairchild, and you can see here that 75 amps of load it can handle, only 30 volts, but look at its on resistance, 0.009 ohms. Right? If you're passing just say 10 amps, that's only going to be 10 milliwatts. 100 amps is going to be 100 milliwatts. So 75, it's only going to be about 75 milliwatts of dissipation when it's fully turned on. So it's not going to get warm. If you switch it very, very quickly, it will, because of the switch through linear region as it's turning on and off. But as far as low frequency, and I'm talking about maybe if you're switching the LED on and off for dimming at say 20 kilohertz, 30 kilohertz, it's not going to be an issue and won't require a heatsink. It's the logic level gate drive. This is one of the indicators that it's great for using with microcontrollers because a lot of MOSFETs need a much higher voltage to start turning on, in the region of maybe 6, 10, even 12 volts in some cases. VGS threshold. In this case, they're measuring at 250 microamps, but again, 1 to 3 volts, right? And then typical 7 milliohms on resistance, maximum 9 milliohms on resistance. That's with 10 volts on the gate source. So remember I mentioned that at different voltages, different things will happen, because there's a voltage amplifier. So at 5 volts on the gate, it's going to have about 12 milliohms. And if you're down at 4.5 volts, it's about 14 milliohms. So it's still, you know, even at 3 volts, which is within its switching range right here, it's still going to have probably under 20 milliohms of fully saturated resistance. So, you know, even if you're passing quite a few amps through it, it's not going to get hot. A little slower to turn on and off here if you're switching high currents with it. So anyway, that's that power transistor. The next one is another switching transistor. This is the one that I was showing you in the picture, this one right here. This one is 300 volts it can switch, as opposed to, you know, 60 and 75. This one was only 30 volts, and the little one was 60 volts. Right? This one is 300 volts, and it can actually switch 110 amps. That's one of the reasons why it's in this kind of package that it's in, because that's a lot of current and a lot of power. So you can see we've got the drain and source available here on 2 separate terminals, which will be your power side of things. And then we've got a gate and source with separate connections, so we don't start introducing high power currents near the gate. You know, I'm sure that these two internally are very tightly coupled, but nevertheless you're not sharing the same connector as what is switching the high powered loads. And if you look at, I think somewhere down here, it shows a slightly different diagram than this typical MOSFET. Anyway, let's go down and have a look. So 24 milliohms RDS on, gate source threshold, 700 watts this one will switch, which is horrendous. It's like more power than most of us will ever need. Okay, here's its gate threshold voltage, right? So this one, these other ones we were looking at were 1 volt and under as the minimum, and then typical would have been about 3 volts. This one is actually 3 volts to start with, up to 5. So if you were trying to switch one of these, you may not be able to do it with an ESP8266 or any other 3.3 volt logic device, not easily, because it is a 3 volt. Now this is still a logic level, I think it's still called a logic level because it is 3 volts. No, it doesn't actually say it here. So anyway, applications for this one are things like DC to DC converters, battery chargers, switch mode, resonant mode power supplies, motor control, UPSs, high power switching applications. So very specifically designed for switching applications. Now one of the other transistors that I've got, this is another MOSFET, looks identical, but this one is a linear MOSFET. It's designed for linear based applications. It's 500 volts at 46 milliamps with a 160 milliohm on resistance versus 24 milliohms. So it's much more on resistance, but it's designed to work in its linear mode. All right, so its power dissipation is still 700 watts. A little bit less voltage, a little bit less current. But if you can think, if it's working in its linear mode, that means that it's not fully turned on. So you'll get a lot of high voltages at high currents being put across the MOSFET, which means it's going to generate a lot of heat. Watts is volts times amps. So if you've got, say, 100 volts, which is well within its specification, and you're passing just 10 amps, nowhere near its maximum current, that's 1 kilowatt of power you're trying to dissipate in this device, right? So you got to be putting it on heat sinks and everything else. Now you're working in linear region 2, so it's not really what we've been doing here with LEDs, but it would be if you were going to be controlling, say, a DC load or something like that. Its gate threshold voltage in this case is between 3 and 6 volts. So it starts at a minimum to be the same, but it's at the other end, it's higher. Now, you vary the voltage between 3 and 6 and more, you can get this device to turn harder on or off. As it say, you can think of it as a voltage-controlled resistor in very simplistic terms. Anyway, I'm not going to dwell more on this one because it's really not what we're talking about here. What I mentioned with the Arduino Uno from its specs with the pins is the fact that its operating voltage is 5, but it actually doesn't output 5 volts, it outputs about 4.8, because again, it's got transistors and things like that dropping some of the voltage. The digital I/O pins, it's got 6 of them, can provide PWM. We were using 1, 2, 3, 4, 5 of them in our example. It says here the DC current per pin is 20 milliamps. If I bring up the spec for an AT Mega 328 data sheet, we'll have a look at the actual data sheet for this. Right, 32K flash, etc., etc. We've gone through all this before. What is important is what the current is per pin. Okay, here we go. Finally found it on page 258 of the data sheet. A lot of information here. So, absolute maximum rating for this microcontroller, DC current per I/O pin, the absolute maximum is 40 milliamps per pin. And if we go down here, although each I/O port can sink more than the test conditions, 20 milliamps at 5 volts, 10 milliamps at 3 volts, this is why I tend to aim nearer towards 10 milliamps, the following must be observed. The sum of all I/O ports should not exceed 100 milliamps. So considering that most ports have got 8 pins on them, 100 divided by 8 is not 20, right? That's only 5, so you're nearer the 10 or 15 milliamps per port. The same for the port B and port D, should not exceed 100 milliamps. And there are more conditions. The sum of port C and port D should not exceed 150. Right, so there's a whole bunch of caveats here about what you shouldn't exceed when you're driving external loads. So, you know, that's why when I ever use these pins, I try to limit the current to about 10 milliamps. That way you don't fall foul of all these other things. If you're trying to make a design that maximizes the use of what the chip can do with minimal components, then sure, you could exceed that, but you've got to go into these data sheets and verify that you're not exceeding some other parameter that is related to it. So anyway, you feel free to have a look through the data sheet for this. I'll provide a link to it again in the description, as well as where you can get these kits from, etc., etc. Anyway, this is long enough now. I wanted to keep it quite short, and I think I've blown that. But I hope you've learned something, how to run external loads with digital outputs, how to pulse width modulate some LEDs with analog writes on the digital pins. And in the next video, what we're going to do is maybe up the ante a little bit and do some RGB. We'll drive an external RGB 10 watt LED, and maybe even a bigger one. I've got a few of those hanging around here, so it makes for something a little more interesting for programming. I'm also going to start introducing some intermediate and advanced programming videos as well, just so that you guys that are a bit more advanced aren't going away because you're bored or anything like that. I want to keep you interested if I can. Anyway, that's it for now. I will see you in the next video. If you liked it, give me a thumbs up. If you don't, well, then don't. But we'll see you again soon. If you have any questions, feel free to post them in the comments.